So today I want to talk about the process and methodology that I've developed over the past year or so for searching for low-level inter-process communication-based vulnerabilities in macOS. I'm going to start by giving you a bit of a crash course in case you're not super familiar with fuzzing or macOS as an operating system and its IPC mechanisms. Once we kind of establish those foundations, we will jump into the attack lifecycle and the process that I've been going through to fuzz these IPC mechanisms. And then we'll talk about kind of next steps and hopefully get you inspired to do some vulnerability research of your own. So let's start at a very basic definition level here, and let's just talk about what fuzzing is. I like the definition of fuzzing as just sending unexpected inputs to a system in the hopes of making something unexpected happen. And I like to define an attack vector as a channel to send that unexpected input to that system. So on modern devices, we have all sorts of attack vectors. Bluetooth, inter-process communications, push notifications, Wi-Fi connectivity, peripheral devices. The world is really your oyster. So as you start kind of looking for a topic to perform vulnerability research in, you can start to enumerate some of these attack vectors. So let's take a look at a couple examples here. If we're looking at, for example, Adobe Acrobat as an application, we can think of the functionality of opening a PDF as an attack vector. If we're looking at attacking maybe Google, we can look at an input query as a potential attack vector. And if we're looking at a smartwatch, maybe that's handling incoming Bluetooth data. So the point is, once we identify these attack vectors and we figure out how to send meaningful input to them, we can start fuzzing or sending that unexpected input to make unexpected things happen. And in the security space, we're generally interested in exploiting those systems. So why would we want to fuzz and send unexpected input? In memory unsafe languages, C and C++, which largely builds most of the infrastructure that we operate on, C and C++ is memory unsafe, so we want to try to trigger a crash. Because depending on that type of crash, we might be able to exploit a memory corruption vulnerability. So examples of this you've probably heard of are buffer overflows, heap overflows, use after free vulnerabilities, double freeze, and memory leaks. So here's an example of a remote code execution vulnerability. And if we just look a little bit, we can see some of these definitions that I'm talking about here. So number one, you see the attack vector in Adobe Acrobat. They're opening a malicious file to trigger this. And then number two here, you see the object prior to performing operations on the object. This is very typical usage nomenclature for a use after free vulnerability. So if we built a fuzzer here, we could write a fuzzer to open a bunch of random PDF documents and kind of programmatically mutate those documents and potentially trigger this vulnerability. So there's a couple different types of fuzzing. The first is, like I just mentioned, mutation-based fuzzing. So this is where we start with kind of a grouping of existing inputs, and then we want to modify them to create new ones and send them to the program. And the hope there is that the existing inputs are valid and will get us kind of deep into the application flow and won't be, they'll be able to bypass typical error handling checks that you would typically see. And then we mutate kind of those valid inputs and we try to make different things happen and explore different code paths within the program. Another approach is grammar-based fuzzing, which is also very valid and has different applications, but this is where we generate inputs based on specified rules. So you can think of maybe you're trying to fuzz JavaScript in a browser. You have a set kind of defined RFC of how that language works, and you can then write a grammar-based mutator to take that kind of RFC into consideration and generate inputs based off of that. So today we're mostly going to be focused on mutation-based fuzzing, which is the approach that I took. Okay, so now let's jump into a little bit of macOS specific background. We're going to start by talking about the XNU kernel. It's the kernel that powers macOS. There's a few different layers here that I want to touch on. The first is the Mach layer. It's responsible for a lot of low-level tasks like thread management, inter-process communication, and memory management. We're going to be focused today on this talk in that IPC mechanism. There's also the BSD layer, which handles more higher-level file system operations and network operations. And then there's IOKit, which is a kind of device driver development framework. Today, we're really going to be focused, like I said, on that Mach layer. So let's define a little bit about inter-process communications on macOS. It turns out processes need to talk to each other on operating systems for a lot of different reasons. Sometimes this is signaling that a network event has occurred, that there's data ready to write, that a thread has completed. There's lots of different reasons that processes need to talk to each other. And there's a lot of ways that they do this. So I've listed a few here. The important thing is that all of these IPC mechanisms on macOS are built off of this one thing called a Mach message. So this is the lowest level IPC mechanism on the operating system, and all these other mechanisms you see here are built on top of it. This was interesting to me in my research because I thought if we can go as low as possible and fuzz the Mach layer, we might be able to trigger a lot of interesting and unexpected crashes. So let's talk a little bit more about how this Mach IPC mechanism works. It is an IPC message queue that is managed by the kernel. So the kernel is in charge of taking in messages and then distributing them to the proper subscribers. And there's this notion of port writes, which is a handle to a port that allows sending or receiving messages to the port. So first is a receive write that allows receiving a Mach port's messages. There's also a send write, which allows sending messages to a Mach port. And there's also this notion of a send once write, which allows sending a single message to a Mach port. And you can actually take a look if you have a macOS system at these Mach ports and the messages that they're sending. You can just use the LSMP utility, and you see here an example. There's a ton of Mach messages being sent constantly by your system, thousands by the second. So they're heavily utilized by the operating system. So let's talk a little bit about how two processes would actually establish a Mach connection. So this typically starts from what's called a bootstrap server. This is a Mach port that's specifically enabled to help establish connections. And by default, all processes are going to have a send write to that bootstrap server. There's also this notion of a Mach service, which is really just a Mach port with a name that is registered with the bootstrap server. So for example, com apple nullcon. And this kind of operates a little bit similarly to how DNS works. So if Alice, say, wanted to spin up a service and then allow people to talk to that service, she could allocate a new Mach port with a receive write and then register her service with the bootstrap server using com apple nullcon. By registering that service name, Alice is giving the bootstrap server a send write to that port that Alice has a receive write to. Now Bob is going to come along and ask the bootstrap service for a service named com apple nullcon. The server is going to say, all right, I have a send write to that Mach port. I'm going to give you a copy of it so you can now send to it. And now Bob can send messages to Alice's Mach port using the kernel as a mediator between those two processes. So let's dig in a little bit more to the structure of Mach messages. So this is the base struct that is used to send these messages. Pretty typical as far as kind of message sending structures go. We have a remote port, which is the Mach port that we're trying to send to. We have a local port, which is the port that we're sending from. We have a message ID, which is used for specific RPC-like functionality. And then we have this kind of nebulous message body field, which you see in the middle there. There's essentially no structure to that data. It's really up to the receiving process how they will interpret that Mach message body, which is very interesting because we can kind of use that to make unexpected things happen when we get into fuzzing, which we'll talk a little bit more in a little bit. When we actually go to send and receive a Mach message, as far as API level functions go, we use the Mach_message function, which you can see right here. That option struct or option type will allow you to specify whether it's a send or receive. And then all of the data itself is confined to that Mach message header T type, which contains that struct within. Okay, perfect. So we've talked a little bit about what fuzzing is, why we might want to do it, what Mach messages are, and how IPC works on macOS. So now we're going to jump into the attack cycle as far as memory corruption goes that I've kind of established and tried to look at throughout this research. First, we're going to talk about abusing Mach messages, and one of the biggest ways that these messages have historically been abused is through two mechanisms. The first is a sandbox escape. So let's say that you have code execution on a Chrome browser. All modern browsers have sandboxing, so you're not going to be able to access a user's system files or kind of move within their operating system. You're going to be locked down to that web process, typically the renderer. So what an attacker will then want to do is pivot out of that Chrome sandbox into an unrestricted context on the user's system. And Mach IPC is actually a mechanism to do this. So the web browser process does need to send Mach messages to other processes on the system. So if we can actually send from that browser process a Mach message and exploit a message handler, we can potentially get unrestricted code execution outside of the renderer process. So this is the notion of a sandbox escape. The other is just a standard privilege escalation that can abuse Mach IPC mechanisms. Say we're running, as an attacker, we have code execution in an unprivileged process. We want to get root access on a user system. We can do a similar process of using IPC, exploit a message handler in a privileged process and perform that privilege escalation. Perfect. So the first step that I took, in this research, I was mostly focused on looking at sandbox escapes. So the first logical step was to try and figure out, okay, given some high impact processes, what are the sandbox allowed communications? So what processes from that Chrome renderer process can we actually talk to? Because those are going to be our attack vectors that we can use to escape from that sandbox. So we can use a tool which was developed by Jonathan Levin. He's got a lot of great macOS research out there that I slightly adapted here. It's called SVTool. Essentially, you can pass it a PID, and it will enumerate all of the Mach services that process can communicate with from an unrestricted context. So from this point, we really narrowed down kind of the attack surface and specifically the services on macOS that we're interested in looking at. We start with kind of all macOS processes, as you see here. Then we just look at the ones that have a registered Mach service with that bootstrap service. And then we can even trim it down further by looking at only the processes that are allowed to communicate from these high-impact services via Mach. I do want to call out just a couple of previous really successful research white papers that have been really inspiring to me in this research. The first one was a Black Hat talk that I was fortunate enough to attend about breaking out of the Chrome sandbox using Mojo, which is another macOS IPC mechanism. And the one that's been most influential was this ret2.io post about a full remote code execution and sandbox escape RCE chain that they developed in Safari, and they disclosed that at Pwn2Own in 2018. This is like a 6-part blog series, so if you're interested in any sort of memory corruption or any of the things I'm talking about, definitely give that a read. It's really great. Okay, so the first step after we've kind of narrowed down the services that we actually want to start fuzzing is finding an entry point. So how do we know where to actually send our inputs to? And as I mentioned in the background, we know that the Mach message function is used to send Mach messages from one process to another. So that's a great start here. And you might ask, why don't we just modify real Mach messages being sent? So we could go ahead and hook onto that Mach message function call with a debugger, for example, like LLDB, and modify the message that is being sent. That's a great approach, and that's actually the first approach that I took as I started performing this fuzzing. There's pros to that. It's simple. It is very similar to the sort of exploit chain if you do find something that you're going to use, because you're going to be calling that Mach message function to send your message. There are some significant cons, though, in that it's very slow. You're at the mercy of applications that you hook onto to send those messages, which there are a lot occurring, but it's not going to be nearly as fast as if you write a fuzzer to send them yourself. There's also many points of potential failure. There's 2 different process spaces that you're dealing with because we are looking at IPC mechanisms, and that makes code coverage difficult, which we'll talk about in a little bit here. And it can be difficult to determine which message actually caused the crash. So with that in mind, what if instead of waiting for Mach message to be called, what if we just wrote a program to call it ourselves? So we kind of cut out sort of this immediate first step, and we get a little bit closer to where the messages are actually being handled. So to do that, we can go ahead and write a program that will just call Mach message over and over and send our input to the message handler that we care about. But could we even get better than that? Could we just call the message handler itself? So instead of sending a message to the kernel and having it send it to the end process, what if we just figured out how to call that message handler directly so we wouldn't have to go through the kernel at all? This would be a lot faster and take off some of the overhead associated with using the kernel to process that message. Like I said, the pros of this, it's very fast. It's in the same process space. So since we're directly sending messages to the process that we care about, we're connected to that process. It's easy to get code coverage and instrument and see what's happening. And it's also very easy to know which input caused a crash and replicate it because the process will just crash and we'll know that. The cons here, of course, it is going to be a little bit different from the end exploit. So we've taken out a lot of this, this flow here that we would normally use from, for example, a Chrome renderer process. And we might have to perform some initialization routines on the process that we care about to get it in a state like it would be running normally on the system. But with that being said, this is the approach that I decided to take for this research, mostly due to the fact that it's much faster to call that message handler directly. Okay, so the next step after we've kind of identified how we want to identify or send input to our message handler is to figure out what do we send. Sending totally random data is not likely going to produce meaningful crashes due to input validation and exception handlers. Developers are trying to prevent against crashes occurring frequently. And so there's a lot of code written in programs that will catch invalid inputs and will not actually allow us to get to meaningful sections of the code where we might find vulnerabilities. So we need to identify examples of valid messages so that we can send them. And this is a process known as corpus building. A corpus is just a collection of those inputs that are valid. Just real quickly, I do want to give a little bit of insight into things to take into consideration if you are debugging and kind of doing low-level system research on macOS. Most of this I performed on a macOS virtual machine. This is critical because you can disable system integrity protection, which is going to allow you to hook on to processes much more easier. It'll give you a bad time if you don't disable this. Also, we're going to want to disable things like report crash and disable sleep so that you can kind of fuzz at will and leave things long running without your system going to sleep. And there's a really great DEF CON talk from a few years back that talks about fuzzing on macOS, which I've linked to here. Okay, so back to generating that corpus of inputs, that data that we want to send that we know is valid to those processes. The first kind of step here is going to be finding the Mach service of interest. So in our case, we care about the services that are sandboxed, processes can communicate with. One that I looked at a lot throughout this research was Core Audio Daemon, which handles all interactions on macOS with audio hardware. It's a highly privileged process, so there's also the potential for privesc here, and it's allowed to receive Mach messages from any process, or from many processes. So the next step is, okay, we know we want to target the Core Audio D service, but now we need to actually find the binary that implements it so we can start reverse engineering it and figure out how to call that message handler. So if we look into this, we see that Core Audio D is registered with launch D. That is the first process that starts on macOS, and it's in charge of starting all of the low-level system services that run within the operating system. And that launch D service then spawns user sbin core audio D, which is a binary. And the Mach server is then handled by the core audio framework, which you can see here. So we attach to that core audio D binary, we do an image list, and we see this core audio framework. Now, I'm like, great, I want to look at the core audio framework. Let's find this binary on disk. You see at the bottom here, though, we try to stat that. There's no such file or directory on the system. Definitely confusing if you're trying to perform reverse engineering and you can't find a binary that is supposedly loaded. So it turns out that in macOS, after Big Sur, most framework binaries are actually not just sitting on disk. And this is the same for iOS as well. There's this notion of the Dillon shared cache, which is essentially a way to optimize the loading of framework binaries on macOS systems. And it sits on your system. It's essentially a highly compact and cached version of these frameworks. But thankfully, you can extract them. There's a great GitHub project that I found that allows you to access that Dillon shared cache and extract those framework binaries that you care about so that you can start actually reverse engineering their functions. So we're using that Dillon shared cache library and extracting all of the frameworks within. So at this point, we have access to that core audio framework. The next step here was then finding the function that implements the Mach receive functionality. And you might be asking yourself, well, isn't that just the Mach _ message function that we talked about earlier? And it is, but it gets a little bit more complicated than that because we actually trapped the kernel when we're receiving a Mach message. And so if we actually want to dump the Mach message that's being sent, we have to get into kernel space. And so I experimented with performing kernel debugging, writing some trampoline code to actually dump those messages in kernel space. There's a really good Fortinet write-up here that I linked to that talks about how you can do that and provides really good steps to do that. But there's quite a few cons from doing that. There's just so many more messages, and it's difficult to isolate the target process that we actually care about. And there's also two-machine debugging required. So you actually need, you can have like a host or a macOS virtual VM, but you have to debug from the host to the VM. So I really didn't want to go through this, so I thought, is there an easier way to just figure out how this is incoming Mach message is being handled? So to figure this out, I started looking into the Mach interface generator, which is known as MIG. It's essentially a Apple-provided tool which allows you to more easily write RPC handlers using Mach messages. So it's known as an interface definition language compiler. It abstracts a lot of that Mach layer and just allows you to call more human-readable functions and pass data in a more meaningful way. So with that in mind, we can actually start to search for some of these MIG-generated subsystems, as they're called. A subsystem is essentially a high-level message handler, and they're normally pretty easy to find just by grepping through the binaries that you're interested in. So we're looking at the core audio framework here. I'm just grepping for subsystem, and you can see a client subsystem and a server subsystem, which are popping up there. There's also a great Hopper script here that I linked to that I modified a little bit for use with IDA Pro, but that's also great at identifying these MIG subsystems. So let's actually dig into what one of these MIG subsystems looks like. This is the server, the MIG server in that core audio framework. And if we just break down a little bit in IDA what this is doing here, there's an incoming message, which is that first argument in the RDI register. And then there's a second argument, which is going to be populated with the return message. This line in the middle there is processing the message ID of the incoming Mach message, and that message ID is then going to be used as an index into the function handler of the MIG subsystem. So we're essentially just getting an offset based on the message ID and calling that RPC function. And you can see in the core audio framework, these are actually all of the RPC functions that are within that MIG subsystem. IDA parses them out really nice. All the RPC functions have this double underscore X to them, so they're really easy to identify. And so once we kind of understand the MIG subsystem and how it's processing those incoming messages, I was able to just write a simple LLDB-based Python script to hook on to that function and then just dump that RDI register so we could see all the incoming messages. So this is a quick little video showing a little bit of how that works. We're going to first find the core audio D process, which is going to load that core audio framework, and we'll then be kind of spinning up that MIG subsystem server. Then we're going to run this Python script that I wrote here to hook onto that hauled MIG server function, and we'll just start saving all the messages that come in. As I'm running this, since we're looking at core audio, I tried to play YouTube, play Apple Music, generate a lot of different audio effects on the system so that we could see different types of messages and hopefully get a lot of different inputs. There's scripts out there that you can use as well to kind of automate this process. For example, there's ones that can click and launch different programs, launch Apple scripts, and potentially generate more interesting Mach traffic. So using this script, I was able to get a really nice corpus of valid Mach inputs that would be sent to the core audio daemon. So the next step is once we have kind of all those valid inputs, we need to actually create a way to send them to that function handler that we care about. And to do this, we need to build what's called a fuzzing harness. So a fuzzing harness is simply code that allows you to send input through an attack vector or call a desired function. So we have our target function, which we were just looking at in IDA here, the HALB mig server function. If we wanted to just write a really easy sort of C binary to do this, it's really simple on Windows. We could use load library and get proc address to call that function. It's pretty similar on macOS as well. We can use the DLOpen API to load the dylib that we care about, and then the DLSym to get the offset to that symbol, and then call that function pointer. But the problem I was having is that the symbol wasn't actually exported, so we couldn't use DLSym to find it. Apple did not want to export this symbol, probably because they want to make it tougher to do exactly the things like I'm doing. So to do that, had to write a custom MacOS symbol parser. This just walks through and kind of enumerates all of the function offsets within the program and interprets the memory addresses, does the fix-ups. That's a talk for another time. But essentially using that process was able to get a offset to be able to call this target function that we actually care about. Okay, so here is just a brief little screenshot showing this harness in action. I'm specifying the library that I care about, core audio, that's going to use DLOpen to get a handle on it, and then the symbol that I care about, and then the TAC-F is just going to be the message that I want to send to it. So that will be a message from our corpus that we generated previously. And we can see we're actually able to print out that Mach message that was in our corpus, send it, and get a return Mach message from that handler, which is pretty cool. Now we see here, we get a result of 1, so clearly something is going wrong here, but we can at least call that function that we care about. Once we can do that, we can now use a fuzzer to integrate with our fuzzing harness to the fuzzer is going to actually generate and mutate input based off of our corpus and send that input through a fuzzing harness to the system and then monitor for any crashes that might occur. So here's a little bit of a diagram of how things work. We have our corpus, which we generated by listening for valid Mach messages. We're going to take in those inputs and pass them to the fuzzer. The fuzzer is then going to mutate those inputs and then using our fuzzing harness, call the message handler. Now, one of two things is going to happen here. Either there's going to be a crash or there's not going to be a crash. If there's a crash, then the fuzzer is going to say, okay, this is a really good input. We care about this. And it's going to save that input. And then it's just going to do that continuously for the rest of our corpus. So this is pretty cool. But there's actually kind of a problem to this. And just as a toy example, let's say that we're trying to fuzz this very simple C function. This is processing a string. So we have an incoming car star. And there's a bunch of if conditions here. First, it checks if the input string is larger than 3. Then it's going to check if the first character is an S. And then it's going to check if the secret string is contained within it. And if it does, it's going to null pointer dereference and crash. But if we're just sort of fuzzing off of a set amount of inputs, we might not even know that we're getting past maybe the first couple of if conditions and getting closer to that crash condition. There's really no feedback for our fuzzer to be able to know that it's traversing those conditional blocks. So for that reason, there's this notion of code coverage. And this is essentially instrumentation that traces a program's execution flow to identify new code paths. So if we look at that picture before, we've added a little bit more in here with this notion of code coverage. So we're still taking in our inputs from our corpus. Our fuzzer is still going to mutate that input and use our fuzzing harness to send it to the message handler. But now we are actually going to instrument that process that we're looking at. And we're not only looking now at if it crashes, but we're also going to look at, is this going down a code path that we've seen before, or did we actually hit a completely new code path? Because if we hit a new code path, if we've made it to the if input, if the first character equals an S, then we care more about that input than if it just balks after the first if condition. So code coverage helps us keep track of that. So if we hit a new code path, then we are actually going to save that input. That's a good input. That got us to a place we've never been within the binary, and we're going to add it back to our corpus. Then the fuzzer is going to continue to iterate on that newly mutated input that we care about. So this concept of code coverage really helps in the fuzzing world. It really helps differentiate from kind of what we call blind fuzzing to a little bit more intelligent fuzzing. So the question is, how do we actually determine code coverage when we're fuzzing a binary? It's really simple to do if you have source code. So you can use things like AFL++, libfuzzer, and gcov. These will automatically grab code coverage information. You compile them into your binaries. But we're looking at black box binaries here. Unfortunately, Apple did not give me the source code for all of these binaries. So it becomes a little bit more difficult. But there are ways around this. You've probably heard of Frida, an excellent dynamic instrumentation framework, as well as one that a colleague of mine at Google wrote called TinyInst. It's a lot more lightweight and can allow you to run things a lot faster, but it can also grab that code coverage information, and it's also cross-platform. For actually interpreting that code coverage information, I really like to use Lighthouse. It's an extension for IDA Pro and Binary Ninja, and it generates output, kind of what you see on the right here. So it'll show us in green the code paths that we've hit, and the ones in white we actually haven't hit yet. So this is very valuable when we're trying to assess how impactful and how well our fuzzing is doing. For actually performing fuzzing and producing crashes. So for my fuzzer, I use the Jackalope fuzzer. This is, once again, written by my colleague, Yvonne Frachik. It's called Jackalope. It's a really nice fuzzer that is also cross-platform and integrates really well with that TinyInst instrumentation framework. I also enabled Apple's guard malloc, which is a way to restrict pages by placing kind of canaries around all memory allocations so we can see more easily if memory corruption is occurring. Then using TinyInst for dynamic instrumentation on the process that we're fuzzing to dump that code coverage information, and then Lighthouse to interpret code coverage. And with that, you end up running a really crazy looking command here, but we're essentially running the Jackalope fuzzer, which we've set up to take in input from our corpus and then use our harness that we wrote to send mutated inputs to the function handler we care about and use TinyInst to get code coverage information from it. So you can see all these processes happening. In that first highlight, you see guard malloc enabled. Allocations will be placed on a 16-byte boundary. You then see the fuzzer running and an exception occurring. Now this is just a C++ exception. This isn't a meaningful crash. And then you also see the instrumentation occurring here. So TinyInst is outputting that code before and code after that crash occurred. So after we have a bunch of time running our fuzzer, there's lots of thoughts about how long you should fuzz before you start changing things up. But we want to regularly check our code coverage. And we can learn a lot actually about how the fuzzing process is working based on the code paths that our fuzzer does and doesn't take. The goal here when you're fuzzing should be to cover as much of the binary as possible. Because if we're not hitting code paths, we don't know if there might be a vulnerability there. An example from Fuzzing Core Audio framework is right here. You can see as I drilled down into the code coverage, I found that for this specific RPC function, we were always going left here. And it was throwing this error called there is no hardware audio layer system. So this was extremely important for me to realize and then kind of backtrack and figure out, okay, why is this happening? It turns out there was some initialization I had to do in core audio to get it set up to properly talk to the hardware, but I wouldn't have known that without this code coverage information, and I would have just been blindly fuzzing without actually increasing coverage. So after we fuzz, we're going to start generating lots of crashes, especially once you start getting code coverage and getting into more interesting parts of the binary. Crashes are going to start occurring a lot. And it becomes very important to differentiate which ones are important or potentially exploitable and which ones are not important and almost certainly not exploitable. So some examples of crashes that we really care about. A crash on a write is very important because that means that we are potentially writing data into memory that we don't control. And this can allow us to potentially write into other process memory or overwrite function pointers and get code execution. We also care about crashes on execution, illegal instructions, heap corruptions, and stack traces where we see things like free and malloc or some of those low-level memory management APIs. Things that are likely non-exploitable, a crash on a read, although this could allow us to perform a memory leak, which can be valuable. A handled exception, so like we saw before, a handled C++ exception, maybe something that's doing input validation. We don't care too much about that. Null pointer dereference, also don't really care about, and a stack recursion crash, we also don't care about. Now this can be a lot to look at, kind of crash by crash, especially when you're generating, on the thousands of crashes. So there's some useful tools that you can use. On Apple specifically, there's a tool called Crash Wrangler, which is really useful. It can kind of run through and look at some of your crash information and determine whether you should maybe check out this more, looking for some of the heuristics that I just talked about. There's another really good one that is implemented in LLDB called CrashMon, which I've used as well. The other important thing to think about here is the reproducibility. So unfortunately, sometimes we produce a crash that had all of these crazy race conditions, and we're not actually able to reproduce it. This is unfortunate, but the reality. And so it is important to be able to run those crashes over and over and generate that crash consistently if we want to have a reliable sort of proof of concept. Perfect. Okay, so let's just take a step back real quick and talk about a little bit of what we've covered. We started with a crash course on fuzzing and Mach IPC mechanisms. We then drilled down a little bit into the attack process when dealing with memory corruption. We talked about identifying attack vectors, generating a corpus of inputs that we can then mutate, writing a custom fuzzing harness, and then triaging those crashes. Hopefully I also was able to highlight some of the common pitfalls that can come up. This was definitely a huge learning process for me and an iterative process of running into a problem, figuring out how to fix it, and dealing with a lot of trade-offs along the way. And I also really hope that I've inspired you to do vulnerability research. The goal here when we've had some great talks talking about spyware and how important these exploits are if they fall into the wrong hands. So it's very important for us security researchers to be able to identify these vulnerabilities before the bad guys do and before they can be used for nefarious purposes like we heard about earlier. So I hope I've inspired you to do vulnerability research. I also hope that we can collaborate, so please let me know if you'd like to talk about this or if this research interests you. Some of the next steps that I'm currently working on in this research is, first of all, increasing code coverage of those Mach IPC handlers. This is kind of including doing some stateful fuzzing, so instead of just looking at a corpus of inputs and sending them off and mutating them, looking at, okay, what is the actual statefulness of these messages? Does one need to come before another? and things of this sort. Additionally, performing some automatic initialization of some of the service binaries on macOS. You saw some of the difficulties that can arise when things aren't bootstrapped properly. So performing some kind of automatic initialization there. I'm also in the process of open sourcing my Mach message dumper and the fuzzing harness. That's taking a little bit longer than expected, but I'm getting approval to do that. And like I said, also always open to collaborating with other researchers or just talking about this stuff if it's interesting to you. So please reach out. I have my Twitter handle and blog linked here, and would love to answer any additional questions anyone has.
Yeah, it's for the recording.
Okay, thank you for this. It was very interesting. Putting aside the crashes and exploiting crashes, just for a second, I was wondering if you considered or if it would make sense to you to also take into consideration the logic attack surface on these message handlers. Like, I'm imagining if these message handlers like they open the opportunity to some like privileged operations, like mounting on file system or executing processor or stuff like that, which may be undocumented, you know, but maybe by reversing those handlers, you might like. Do you consider it, or do you think it would be interesting?
Absolutely. Yeah. Sorry, I can't quite see you with the microphone here.
It's the worst place.
Yeah, absolutely. I think I think that's a great idea. And that's definitely something that I've tried to do a little bit. It does require a lot of manual reverse engineering, especially, like I said, there's no source code. There's no symbols typically in these frameworks. So figuring out that like interesting functionality can be difficult, but it's definitely something that I'm pursuing. And if you can, you know, like you're saying, if you can trim down your fuzzing to only RPC functions that might later execute like privileged operations, then yeah, you've narrowed your attack vectors and attack scope a lot, and that can allow you to get more rapid results. So definitely.
Hey, thank you for the talk. That was interesting. I do have, here. Sorry. So you said, right, coverage-based fuzzing, right? Mm-hmm. But when you are talking about opaque messages, I don't know, like, changing what will actually increase my coverage. So is there any heuristic as to, you know, maybe some way to interference based on that this code path actually will be triggered by this change?
Right. Yeah, that's a really great question. I do know that there is, I know there's some research, and there was actually a really interesting Nullcon talk that I went to in January in DC that was talking kind of exactly about that, about how do we know, based on one input, what was the exact code path that we hit. Because you're right, when we look at this diagram here of Lighthouse, this is all of the inputs that we've ran. You know, this could be thousands of inputs that generated this code coverage, but we might care about, okay, this input was actually responsible for getting us here, and then pivot off that. So to my knowledge, there's not a tool that allows for that easily. If anyone is aware of that, I would love to talk. But yes, I think that's super impactful. Did that answer your question?
Question I have.
Yeah.
So, like there is pretty active effort going on in, let's say, writing things in Rust, which kind of solves most of the memory safety issues. But this fuzzing kind of requires that something crashes, right? And Rust will sort of at least guarantee that nothing crashes. So right. Then is fuzzing still a viable option to find these vulnerabilities?
Yeah, also a great question. I think it is. It's definitely, it gets trickier when you're not, crashes are just such a great heuristic to something wrong happening. So, you know, if everything was written in Rust, I think things become a lot more secure. There's certainly still things that you can look for, potentially like accessing new interesting operations or hangs that can occur. It might kind of require a shift in what those heuristics look like. But yeah, I think it would make things a lot easier.
Yeah, you used guard malloc for detecting the crashes. So is this similar to address sanitizer? Like, does this the temporal safety and spatial safety? And would it help some other sanitizers like undefined behavior sanitizer or threat sanitizer to hook them in, or?
Yes, yeah. So it's very similar to address sanitizer. It doesn't give you quite as great of a drill down as ASAN does, but yeah, I'd say it's essentially a macOS interpretation of ASAN.
With some other methodologies, sometimes you get a crash inconsistently. You mentioned this briefly with race conditions, but sometimes it's a matter of having multiple messages somehow lead up to that crash. But of course, if you replay the last message that you have sent, it does absolutely nothing because it's something else that has messed up the memory before. Is this something you come across with your methodology? How do you deal with it? Because I have no idea.
Yeah, it's a great question. It's certainly a difficulty. I have been thinking about how to tackle this, and that's part of what I was talking about with looking at statefulness of Mach messages. So, figuring out like if there's certain messages that should be sent before another one, kind of like you're talking about. I'm still trying to figure out the best way to do that. I've had some kind of primitive attempts of logging that information in a matrix and keeping track of, okay, we reach new functionality after these two messages, and then we sent this one. But it's become very complex very fast, and I don't have a great solution for it.
I do have a second question, which is more like, what sort of, results did you have? You showed how to do it. I don't know if you can talk about any of the results,
I can't talk about all of the results. I can say I've generated a lot of crashes. Most of them have been unexploitable. There's some that I'm still looking into, but nothing that I have reported thus far. No problem.
All right, I think we're done. There's a lunch break now. Thank you for the talk.
Thank you.